In our most recent lecture, we talked about Gibbs free energy and how this was a measure of where an equilibrium lies. Is the forward or backwards reaction favoured, i.e., is the reaction spontaneous? Here's another reversible reaction. This is isooctane, one of the main components of petrol. In the presence of oxygen, we get a combustion reaction, producing carbon dioxide and water. The Gibbs free energy value for this reaction is a huge minus 1000 kilojoules per mole. Clearly, this shows us the products are more stable, and this should be a spontaneous reaction. Right? Wrong! Here is a small sample of isooctane, and given the amount of oxygen in the air, you would expect this to ignite and burn everything down around me, but as you can see, it's very much not on fire. And that's probably a good thing for all our cars too. This system is not at equilibrium. In fact, there's no reaction happening here, and everything is sitting completely to the left-hand side of our supposedly reversible reaction. What this reaction needs to occur is an input of energy, such as a little spark. Now, I could provide that with this lighter here, but I'm not wearing any PPE and I don't want to set fire to the place that I'm recording this in, so let's not do that. No. Instead, it's time for a gratuitous analogy. I said that isooctane can be used to power cars, and one of my most favourite cars of all time comes from my second favourite time travel franchise. I'm talking, of course, about the DeLorean from Back to the Future. If you're expecting a clip of the film just then, I'm sorry to disappoint you, but I can't afford the rights for that. What I can afford, though, is an actual DeLorean made of Lego. Okay, so the DeLorean in the films isn't powered by petrol, it has some kind of fancy nuclear reactor, but let's not focus on that and instead on the coolest thing it does, which is to travel through time.
Marty, it's a disaster! Something is terribly wrong with time! The 21st century is on track to become a nightmarish dystopia!
Oh, geez, Doc, that's heavy. What happened to all those hoverboards and self-lacing shoes we saw the last time we visited the future?
I don't know, my boy, but something tells me that orange abomination we saw on those weird flat televisions had something to do with it. Perhaps if we get back to the 1980s, we can change the future for the better.
Okay, so Doc Brown and Marty need to escape this hellish future that they're in, and to do that, they need to power up the DeLorean to
88 miles per hour!
Exactly. So what we have here is a vehicle that is capable of time travel. It doesn't obey the fixed linear laws of time, so we could say that it is temporally unstable. However, it doesn't just fall through to 1885, 1955, 2015, or whenever. It has to get to that sweet speed of 88 miles per hour to do so. It has to have the correct amount of kinetic energy in order to smash through the time barrier, and it only gets that when it's going at 88 miles per hour. It also needs to hit time head on. It needs to be driving forwards, or it isn't going anywhere. Oh, look at that. We're back in the 80s. But to bring this back to chemistry, we can propose an equation of sorts for what's happened here. Let's call our reagents the DeLorean and time, and we'll say that the product is time travel. But we can't get there unless we put in some kinetic energy, so that when the DeLorean hits time, the reaction is activated. We could therefore describe the system of DeLorean plus time as temporally unstable but kinetically stable. Okay, let's think about that isooctane reaction again. We said we needed to give it a spark, an input of energy, in order to get from our reactants to our more stable products. Our system is thermodynamically unstable. There should be a reaction, but there isn't because it is kinetically stable. It needs that input of energy to get over a barrier in order to get to the product. That barrier is known as the activation energy, and it is what prevents a lot of theoretically spontaneous reactions from happening. Just like the DeLorean hitting time, molecules have to have the right amount of kinetic energy when they collide with other molecules in order for the reaction to happen. We also said that the DeLorean needs to hit time head on. And it's the same with molecules. They have to collide with the right orientation. If they don't, no reaction is going to occur. There's not so much we can do about orientation, but activation energy is something we can influence. What we'll be looking at in our next lecture is how we can consider activation energy in our organic reactions. How does it relate to things like temperature, catalysts, solvents? What are these things called rate equations and why are they important? And what about these kinetic versus thermodynamic products? It's all to do with stability.